Okay, graphing sine and cosine functions. So today we're going to learn how to sketch the graph of a sine function and a cosine function, and we're also going to talk about characteristics of each of these functions. So some new vocabulary words that we're going to talk about today is, the first one is called a sinusoidal curve, and this is just a name given to a curve that is going to fluctuate back and forth. So something that is a curve that oscillates repeatedly up and down from a center line. So something that's continuing over and over and over again. So this center line that it fluctuates from or oscillates from is called our central axis. Or it could be called the horizontal axis. Or another name for it sometimes is called the midline. Okay, so all of these terms all relate to the same thing. And then from there we have the definition of a periodic function. So a periodic function is a function whose graph repeats regularly over some interval of the domain. So whether that interval continues forever or whether we're given a certain interval, it's a function that repeats itself. So looking at this sinusoidal curve, obviously this graph is repeating this pattern over and over and over again. Okay? And so the reason why we called it a periodic function is because within the function we have this thing called the period, which is the length of the interval of the domain over which a graph repeats itself. So the horizontal length of one cycle on a periodic graph. So if I were to draw one cycle of this graph, this would represent one cycle. So the distance from here to here would represent the period. Okay, so that's the interval of the domain over which the graph repeats itself. So examples of periods. So when we talk about periodic functions, we're talking about things that repeat itself over and over again. Okay, the biggest one is time, right? And time could relate to lots of different things. An example is we could graph our daily routine. And what would be the domain of that, or the period of that daily routine? Would be every 24 hours, right? So most of us have a fairly scheduled daily routine, what we do at certain times of the day, and when that occurs would have a period of every 24 hours, right? We get up and eat breakfast roughly the same time of day, that would have a period of 24 hours. We start our school day at 8:35, that would represent the period of our day. Okay. What else? So pretty much anything that relates to time, like seasons, right? Seasons have a period. The period would be represented by, they come and go every year, so 365 days, right? Like fall starts on September 21st, right? And so it's not going to start again at that point until the following year, 365 days later. So the period of our seasons, tides of an ocean, right? The tide comes in and out every approximately 12 hours, right? So the period of tide of an ocean. Sound waves, right? So when we hear sirens go off on our streets, that's a periodic function. Anything that goes around. So a common example that we refer to is Ferris wheels, right? A person gets on a Ferris wheel and it rotates a full rotation. Okay, what would be the period of that? Well, it would depend on how fast the Ferris wheel is moving. Any wheels. So wheels on your vehicle, wheels on your bike, wheels on a gears, anything. Okay, so anything that's repeating itself over time is going to have some kind of period. Okay, so besides period of our function, so period kind of relates to the domain of our function, we have this new definition called amplitude. And this is the maximum vertical distance the graph of a sinusoidal function varies above and below the horizontal central axis of the curve. So we're always comparing the amplitude, not the entire function, but from its central axis. Okay, so if we go back up to our curve here, here's our central axis. This vertical distance represents our amplitude. And often we call this the A value. Okay, so and the formula to find amplitude is we would take our maximum point, take away the minimum point of that, and then average those two values out, so divide them by 2, and then that'll give us this distance. Okay, or sometimes you can clearly see where that central axis is and find your amplitude that way. Okay, all right, so we have 3 quick examples here that we're simply going to determine the period and amplitude of each of the following periodic functions. So looking at this function, to figure out the period, I want to figure out where a full cycle starts and ends. So if we look at this, right, this would represent 1 full cycle. So the period of this function would be 8. The amplitude, the x-axis is very clearly the central axis. And so the amplitude would be this distance between the central and the maximum, or the central and the minimum, either or. So amplitude doesn't necessarily have to always go to the maximum. You can go to the minimum. So the amplitude here would be 10. Okay, question B. Again, I'm going to draw a full cycle of my graph. So when I draw a full cycle, I tend to always start on my y-axis and then figure out where the graph is ending after that point. So if I start here, I need to get back to the most or the smallest point on my curve to complete a cycle or find the next minimum point. So if I were to follow this graph, right, there is 1 cycle. And so the period of this graph would be 6. Our amplitude, so a couple ways you could do this. Your amplitude, you could use the formula by taking your maximum, which is at 6, subtracting your minimum, which is at -2, and dividing by 2. Or you can kind of gauge where your central axis is going to occur here. It's definitely not the x-axis in this case. So our central axis is always falling halfway between the minimum and the maximum. So this is our central axis, and our amplitude is the distance from the maximum to that, which would be 4 units. So whether you use the formula or kind of visualize or draw in your central axis and go from there, it's up to you. Okay, question C. Again, I'm going to start on my y-axis to figure out my period. I'm going to sketch 1 cycle, which would be this, because this is where the point I'm going to repeat that cycle again. So the period of my function in this case would be 10. My amplitude in this case, again, you could use your formula, right? 6 minus 2 divided by 2. Or you could visualize the central axis. Your central axis is at 4, so the amplitude here, this distance from 4 to 6 would be 2. Okay. All right, so fairly straightforward, period and amplitude. Okay, so from here what we're going to do now is we're actually going to learn what our base sine function looks like, because tomorrow we're going to start to transform these functions. Okay, so our sine function is directly related to the relationships or points on our unit circle. So basically what we're doing is we're taking our unit circle, we're rotating around it, and we are going to plot each of those points now on a actual coordinate grid. So your x-axis is always going to represent your angle, and your y-axis for the sine function is going to represent the ratio value that it relates to on the unit circle. So on our unit circle, when sine of x at 0 degrees, our ratio value would be 0. So we're going to write all these exact values out, and then we're going to give the approximation values. Okay, so as I start to do this, rotating around my unit circle, right? So the reason why I want approximation, because I want to start to plot these points on my grid so that I can visualize what this graph is going to look like. So if I start to plot these points, 0, 0 at 30 degrees, my ratio is 1/2. At 60 degrees, it is root 3 over 2, which is about 0.87, about there. 90 degrees, it's at 1. 120. And so on. So I'm just going to quickly take a minute to write in all of these values, and then we're going to plot each of these points. Okay. Okay, so I've already kind of finished those points here. So I'll just quickly show them to you rather than having to write them all out. Okay, so I rotated in the positive direction from 0 to 360, and then rotating in the negative direction from 0 to negative 360, we get all of these values. Okay, so what we want to do now is we're going to take all of these values and we're going to plot them on our coordinate grid. Okay. So at 120 degrees, this value is now at 0.87. 150 is now at 1/2. At 180, it's at 0. 210, it's at negative 1/2. Negative 0.87. Negative 1. Negative 0.87. Negative 1/2. And then back at 0. Okay, and then these values are going to kind of repeat themselves in this direction as well. Okay, so you can clearly see what's happening to this sine graph as for every full rotation, right, I'm getting a curve that looks something like this. It's a general curve that fluctuates periodically over time. So if I were to talk about the characteristics of this function, the period of this function of a basic sine graph is going to be 360 degrees, right? Because that represents one full cycle. Or in radians would be 2 pi. The amplitude of our basic sine function would be 1. The x-intercepts. Well, because technically this graph continues forever and ever and ever, it's never going to end, our x-intercepts are occurring at 0, 180, 360, and so on. So they're occurring every 180 degrees. So I'm going to say, rather than listing all of them, I'm going to write a general expression for all of our x-intercepts to be 180n, where n belongs to the integers. Or, if this was in radians, would be every pi, n, where n belongs to the integers. Okay, because sometimes we're going to graph this in terms of in where our x-axis is in degrees, and sometimes we're going to graph it in radians. You have to be able to go back and forth. The y-intercept in this case is 0, 0. The domain of our sinusoidal function should be all real numbers. The range of our sinusoidal function should be greater than or equal to 1, but less than negative 1, but less than or equal to a positive 1. Okay, so just a quick little note here. When we think of a starting point, I always think about a starting point on the y-axis. So the start point of our graph is at 0, 0. So this is kind of an important point to remember, because then once we start transforming things, we always want to have a good indication or idea of what this base function looks like. Okay, so this is sine function, y equals sine of x. Okay, all right, so now let's look at what the cosine function is going to look like. So again, I am going to start rotating around my unit circle. So as you can see, instead of working in degrees, I've now changed this to radians, because you could work in both radians or degrees. Okay, so all of these angles really relate to our degree angles, but they are radians now. So we're going to list these coordinate points again on our unit circle that is relating to these angles. So cos of theta, or cos of x at 0 degrees is 1. Cos at pi over 6 is root 3 over 2. Cos of pi over 3 is 1/2. At pi over 2 is 0, negative 1/2, and so on. So we can rotate all the way around our circle, and we eventually get both in the negative and positive direction, and we get this table of values. Okay, so I'll just hide this for now. So here's our table of values. Now we're going to use each of those points, okay, to plot our graph. Maybe I'll just finish off these values. I'll just put the decimal places here, just so I have them. Okay, so now if I'm going to start plotting this graph both in the positive rotation and a negative rotation, when x is equal to 0, which is 0 radians, my cosine ratio is 1. So the graph is going to start here. And then at pi over 3, so if you notice, right, this is going to represent 90 degrees. This would be a pi over 6. This is 2 pi over 6. And this is 3 pi over 6. So now it starts to get a little tricky in terms of how you plot these on. You got to always look at your scale with radians. Okay. So at pi over 6 would be 0.87. At pi over 3 would be 0.5. Pi over 2 is 0. This is negative 1/2. Negative 0.87. This should be at negative 1. Negative 0.87. Negative 1/2. 0. Positive 1/2. Positive 0.87. And 1. So then I'm going to repeat this same process with the same points on the other side if we rotate in the negative direction. So at negative pi, our value should be negative 1. At negative 3 pi over 2 should be 0. And so here's our graph. So this graph looks very similar to our sine graph, and it's almost identical, right? And they could be identical once we apply some transformations to them. Okay, the only difference is the starting point, right? And our x-intercepts. So if we talk about the period of this function, what is the period of this function? So if I draw one cycle, the period would be 2 pi. or in degrees would be 360 degrees. The amplitude of the function would still be 1. The x-intercepts, okay, are going to be a little bit different. So our x-intercepts, our first x-intercept is at pi over 2, and then 3 pi over 2, and so on. So our x-intercepts still have a difference of a pi. They occur every pi radians, but they don't start at 0, 0. So we have to include this first x-intercept at pi over 2, or 90 degrees, plus pi n, or plus 180 n, where n belongs to the integers. Oops, sorry. Okay. All right, the y-intercept. So this is also a difference in there between the sine and cosine graph, sorry. Okay, so the y-intercept is 0.1. The domain is going to be the same as the sine graph. The range is still the same as our sine graph. Okay, and then a note here is, where does our graph start in this case? So on the y-axis, the start point of the graph is at 0, 1. Okay, rather than at the origin, it's starting at 0, 1. So these are kind of key characteristics that we want to try to remember. Okay, and then that is our base function, sine and cosine graph.